Hi there, welcome to this lecture series on matrix algebra. This is lecture 29, part 1. The topic will be on symmetric matrices, and in particular we will explore properties of the eigenvalues and the eigenvectors of symmetric matrices. Let's get started. First, let's do a quick review on eigenvalues and eigenvectors of a general matrix. Let's say A is an n by n square matrix with real entries. Then we can form the characteristic polynomial, let's call it P, of lambda, which is the variable here, and this is the determinant of the matrix A minus lambda times identity. And once you work out the determinant, and you will see that this will be a polynomial of degree n, and then if you factorize it into all the roots lambda 1, lambda 2 to lambda n, then you can write it as this product form. So we see that we will have n roots. A few things to keep in mind is that in general, the eigenvalues might be complex numbers, even though the matrix has only real entries. And this fact you can already observe for a 2 by 2 matrix. And regarding eigenvectors, in the case where the eigenvalues are multiples, meaning they are repeated, then one may not be able to find a basis of linearly independent eigenvectors. And we have covered that earlier in this lecture series. Now let's consider the case where the matrix A is symmetric, meaning that A transpose equals A. In this case, actually, we have some very nice properties we want to explore in this lecture. So here we have a theorem. Let A be an n by n symmetric matrix with real entries. So be careful the assumptions of the theorem. That's where we start, and then we can claim the following. First, all the eigenvalues are real numbers. And second, regarding the eigenvectors, one can always find an orthonormal basis of linearly independent eigenvectors. So here it says that first of all, a set of linearly independent eigenvector would always exist in this case, and furthermore, that beside being linearly independent, and these vectors will be orthogonal to each other, and then you can normalize it and have an orthonormal basis. One can consider maybe a 2 by 2 matrix to start with. Here everything is simpler. We can write everything out explicitly. So let's say in the general form, A is a 2 by 2 matrix with A, B, and C, D. And we can find the polynomial, the characteristic polynomial P lambda, by computing this determinant, which is this times this minus this times that. And you can open it up and write it out in a polynomial of degree 2 in lambda. So you have a lambda square, and then the lambda to the power 1 and the constant term. And you collect them, you'll have that. And then you will see that this term here is actually the trace of the A matrix. It's A plus D. And this term here is the determinant. That's AD minus BC here. And we can find the eigenvalue in general form by the quadratic polynomial for that, and the roots form, okay? So, and that will be negative of this plus minus square root of this guy square minus 4 times 1 and the constant, the whole thing divided by 2. So that is, we already know all that. Let's now consider this quantity here in the square root. It's often called the discriminant. For that thing, if we open this up and open this square up and then combine that, and then we see that a plus d square minus 4 times ad changes into a minus d square, and then we have a plus 4 times bc. So we know if this quantity is bigger than or equal to 0, then my eigenvalues will be real, otherwise we'll have complex eigenvalues. So we see that if A is symmetric, that means B equals C, then 4 times BC is just 4B squared because C is just B, and which is bigger than 0. It's non-negative. So this becomes a sum of two non-negative terms, so this capital delta is always bigger than or equal to 0. So we conclude that there are two eigenvalues that are real. Now let's do a quick review of complex numbers and vectors. So if z is a complex number, a plus ib, a is real part and b is the imaginary part, then we have the complex conjugate of z with a bar on the top, which is changing the sign of the imaginary part, so a minus ib. And then if z is real, that's equivalent to say the imaginary part is 0, and then this imaginary part is 0, then that's equivalent to say z equal to z conjugate. And then there is the inner product of two vectors with complex entries, therefore is defined as the following. So inner product between v and w, these are two vectors of the same length and column vectors. That will be the conjugate of v transpose times w. Take a quick example. If say this is my v here and this is my w, they are both with complex entries, then what is v in the product w? Well, that will be the conjugate of v transpose times w. So it will be conjugated, so we'll be changing the sign of the imaginary part and then to the inner product. So this will be 1 plus 2i times 3 minus 5i. And then the second will be positive 3i times 2 minus i. So one can work out what that is. And then you can use that to define the norm. The norm square is v in the product itself. So the norm will be the square root of that, right? So that means I will do the v transpose. Sorry, typo. There shall be the conjugate of v transpose times v. And then we will get 1 minus 2i times 1 plus 2i. And then positive 3i times negative 3i. Okay, if you work that out, you get a real number, which is 14. So the norm of v will be square root of that, so it's square root of 14. Okay, so this is a very rough review. So let's treat the claim that eigenvalues of a symmetric matrix are real and try to prove it. So what is the assumption here? So we're assuming that A is a square matrix and it's symmetric with real entries. And then lambda is an eigenvalue of A and V is a corresponding eigenvector. If we have that, and then we would like to show that lambda is a real number. So we are not making any claim about the eigenvector. We don't know if that can be complex or real. So we assume in general it's only in Cn. So, and then we want to show lambda is real. Now let's first compute this quantity here. Conjugate v transpose times A times V. So v is a column vector, A times V is a column vector, and this is a row vector. So this in the end becomes a number. So what does that become to? So we know that we're assuming v is an eigenvector, so A times V is just lambda times V. So we can put that in and we have this expression. And then here lambda is a real number, then we can move it to the front. So we have lambda times v transpose, v conjugate transpose times v. And then we know that v conjugate transpose times v is just the norm of v square, which is a real number. Taking this identity we have just derived, that is, this here equals that, and among all these expressions, we know that this norm square is a real number. So we're going to take conjugate on both sides, and we will keep the inequality. So conjugate of this, with the left hand side here, would equal the conjugate of that. And since this is real, so we're just taking conjugate of lambda. So now it remains to show that these two expressions are equal, meaning that the two left hand sides equal each other. So this left hand side is the same as this left hand side. Is that true? Well, indeed, let's compute. So the conjugate of these three products, we can use the property that the conjugate of the product is the product of the conjugate. And then we can rewrite this. So this would equal to, we would take the conjugate of each. So the conjugate of v conjugate is v itself, transpose. And then A is has real entries, so A conjugate is just A, and then V conjugate. And now we use the fact that this becomes a scalar number, because we see it equal to something like this. If it's a scalar number, then we can take transpose of this number and it's itself. So this will equal to the number, the same number transposed. Now we have the last step. This is the transpose of product. Then we can write it as the product of transpose, but taking the product in reverse order. So we would take this guy first and transpose it, times A transpose, which is A because A is symmetric, and then V transpose again, which is just V. Okay, so we see that we have shown that this quantity here equal to that quantity, meaning this equal to that. And then you must conclude that the right hand side here must equal to the right hand side here. Well, if this equal to that for this non-zero vector v, then you must conclude lambda equal to lambda bar, the conjugate of lambda, and therefore lambda must be a real number. Now let's look at properties of eigenvectors of a symmetric matrix. So first we have shown already that all the eigenvalues are real. So, and then by solving this equation, the system A minus lambda identity times V equals 0, that's how you find the eigenvectors. If all the entrants here are real, then the eigenvector V will also have only real entrants, because in this solution here, there's no way you will create any complex number with a non-zero imaginary part. So the first property regards eigenvectors of two distinct eigenvalues. Now let's assume that Vi and Vj are two real eigenvectors of a symmetric matrix A, corresponding to two eigenvalues lambda I and lambda j, and they are distinct. That means they don't equal each other. If that's the case, then we claim that Vi and Vj are perpendicular to each other. Let's offer a brief proof for that statement. So basically we need to show that the inner product of these two vectors are 0, right? So let's do this computation. So we compute lambda I times Vi dot Vj. And here we use the dot to denote the inner product. So And we can combine lambda I with vi and use the identity that ai times vi is lambda I times vi because it's the eigenvalue and eigenvector. So we can write this one as a times vi. Okay, so and then we can write out what is this inner product. This inner product is this transpose times that, and then this transpose we can transpose each and then do the multiplication after, and then we have to reverse the order. So we'll have vi transpose times a transpose, which is this guy transpose, times vj. And then a is symmetric. A transpose simply equal to a, so we put a here. And now we see we managed to write a together with vj, because vj we know is also an eigenvector of a, but with a different eigenvalue, right? So vit times that is just the vit inner product a times vj. And then we can write a times vj as lambda j times vj, because it's an corresponding eigenvalue is lambda j. And we can move the lambda j to the front, so it's lambda j, and then inner product vi times vj. Now take a pause and see what we have derived. We have derived that this expression here equal to that expression. And in there we see that vi inner product vj appears at both left hand side and right hand side. And then we have a lambda I and we have a lambda j. So under the assumption the eigenvalues lambda I and lambda j are distinct, so we know they don't equal to each other. So this number does not equal to that number. And then you want this product equal to that product, and the only possibility will be this number here, and the same as this number, they must be 0. So vi in the product vj must be 0, and proving that vi and vj are perpendicular to each other. So we have proved this very nice property about symmetric matrices and the eigenvectors that corresponds to two distinct eigenvalues, that they are all perpendicular to each other. I do want to emphasize the assumption that this is true where lambda I and lambda j are different. And this is a good place to take a break, and in the next second part of this lecture we will look at cases where you have repeated eigenvalues, and then we will look at examples and some other interesting properties of a symmetric matrix. Okay, so I hope you enjoyed this part, and I'll see you soon.